Have you ever taken a filled balloon and put it in a freezer? You should try it sometime. The balloon will shrink and get quite a bit smaller in the freezer. Then you take that balloon out of the freezer, put it on the table, and the balloon will start to expand again. This is because the size of an object is dependent on temperature. In this video, we're going to talk about thermal expansion, in other words, the change in size of an object due to changes in temperature. We're going to start off talking about linear expansion, that is expansion just in one dimension. So linear expansion occurs when an object is heated. If an object is cooled, you're going to get linear contraction, meaning it's going to get shorter. Now, how much an object changes in length depends on three things. First of all, it's going to depend on how much it's heated or cooled. It's also going to depend on its initial size. If you have a shorter object, it won't expand as much. But if you have a longer object, it will expand a lot more. The third thing that linear expansion depends on is what the material is made of. So this character, the Greek letter alpha, we are using to symbolize the coefficient of linear expansion. Okay, now remember this delta symbol? If you don't, here's your reminder. Delta means final minus initial. So that means that we're talking about a final length minus some initial length. And that's going to equal the coefficient times the initial length times the change in temperature. Well, if we solve for your final length, then you end up getting this equation here. So the final length of an object is going to equal its initial length times 1 plus the coefficient of linear expansion times the change in temperature. So that's linear expansion, expansion in one dimension. Let's talk about expansion in three dimensions, which we also call volume expansion. So it's very similar, but the difference is that you can't really expand a liquid or a gas linearly. If you try to heat up a liquid or a gas, it's going to expand in all directions. It's not going to go in one direction only. So volume expansion works for solids, liquids, and gases. We go through the exact same process of calculating it, and we get the exact same equation. The change in volume is equal to some coefficient of volume expansion times the initial velocity times the change in temperature, which if we solve for our final volume, we would get our initial volume plus times 1 plus beta times the change in temperature. Now, what are these alpha and beta values? Well, like I said earlier, they are a property of the material itself, and their values have been found for you. Here in this table, 13-1, which is in your textbook, it lists the coefficient of linear expansion and the coefficient of volume expansion for a variety of substances. So you can see all your solids here. Only solids work for linear expansion. Liquids and gas will not expand linearly. They will only expand by volume. And then you have your coefficient of volume expansion, which does include liquids and gases here. Just a quick note on water. Water is really different. According to the equation of volume expansion, if you increase the temperature, the volume will increase. If you decrease the temperature, the volume will decrease. That's just how it is. But water is different for some reason, and I could explain why in just a second. Water, as the temperature of water decreases, yes, the volume does decrease, but right around -8, -6 degrees Celsius, the rate at which the volume decreases changes. And here at +4 degrees Celsius, things go really crazy. Now, as the temperature gets colder, your volume actually increases. Well, here is a great way for you to actually see this at work. Remember that density is mass divided by volume. So as the volume decreases, your density increases. So as the temperature drops, your volume decreases and your density increases. But once you hit that 4 degrees line, all of a sudden the volume starts increasing, so your density decreases. So if you put a block of ice, an ice cube, in a glass of water, what's the ice cube going to do? The ice cube is going to float. Why? Because it has a lower density than water. Kind of interesting and actually pretty important. This is very important because if ice, if water followed the normal behavior and um, followed this principle that if the temperature drops and the volume drops, then the density would increase. And as it increases, ice would become more dense. Well, then let's say we have a lake. You form an ice chunk. That ice would float to the bottom, and you'd get this big block of ice at the bottom of a pool, and the lake would get really, really cold, and pretty soon the entire lake would freeze solid, which is not good for things like fish and other animal life that's in the water. That would not be good. So that's not what happens, thankfully. What actually happens is let me draw it in the same place over here. So here's your surface of the water, and there's the bottom of the lake. The ice, which is less dense, stays on top, which actually insulates the water underneath, keeps the water underneath a little bit warmer, so that fish and other aquatic life can actually survive quite happily down there. So yeah, just kind of a random little important thing about this weird behavior of water. Now let's go back to thermal expansion. A material might be fixed at its ends, in which case, as its temperature changes, it wants to expand, but it can't. It can't expand because of the fact that its ends are fixed. It's then going to start experiencing some compressive or tensile stresses. You're not going to be tested on this. This is just for your information. These compressive and tensile stresses can be measured by these equations using Young's modulus back in chapter 9 of your textbook. So you can find that information there.